Okay, so we are going to be going over Chapter 2, Single Area OSPF version 2 for CCNA, course number 3, Enterprise Networking, Security, and Automation version 7. So there's quite a bit. There's a lot of material in this. Fortunately, most of it is, or a good chunk of it, is review to a certain extent. So we're just going to be taking a little bit of a deeper dive. And then I'm also going to be going over and showing a little bit more of, again, demoing how to do OSPF in version 2, kind of get that configuration going. So um, let's get into it. So, like we kind of talked about overall for our routers, when we're configuring OSPF version 2, there will be router IDs that we do have to kind of associate with our devices. These router IDs determine the designated router, backup designated router, and DR others, or also known as druthers. So we can get these, and these router IDs are assigned in a couple of different ways. They can be assigned manually, where we, in the OSPF configuration, actually specify what the router ID is. And again, remember our router IDs are in an IPv4 format, so it's a 32-bit number. With the lower the number, meaning the less important the device, a higher number, the more likelihood you, or the the better. Basically, the higher the number, that device likely becomes the designated router. Second highest becomes the backup designated router, and all the others are DR others. So that's the first way, is manually assigning it an OSPF configuration. The next way that we can configure it is based off of loopback interfaces. So remember, a loopback interface is a testing interface that we might use for, say, simulating a connection out to the internet without actively having one. Now, that interface, the purpose of setting that up is it is always in an up and up state. It's a simulated interface, it's a virtual interface. It doesn't actually exist. So I can't unplug that cable, causing it to go down. The only way I can bring that interface down is by going into it and then manually turning it off with a shutdown command. So, because of that, that's a backup way for getting our router ID, is through the loopback address. Now, our third way, and this is kind of the default way that most devices will grab their IP address, is it will just take the IP address of the highest IP address of a current up and up interface. So if it fails grabbing an IP address from manually having a router ID set, so if there's no router ID set, it moves to step 2, which is to check and see what's the highest IP address on loopback interface. If there's no loopback interface, then it moves to looking at, say, like if we're on router 2, it'll check, say, gigabit 00 or 001, compare the two addresses, and then go, okay, which one's the highest one? 10.119 is the highest IP address, so 10.119 would become the router ID for router 2, as long as both of these interfaces were currently in an up and up state. So that's how it goes through and defines kind of its router ID. So configuration wise, I've kind of set up just a basic network here. So I've just set up IP addresses on all the interfaces, and just gotten all the interfaces turned on. I haven't done any OSPF configuration, so right now I just have LAN connectivity. So again, that just means I can ping within my network, but I cannot go to a different network. So if PC0 tried to ping to router 1 or over to PC2, that traffic would fail. I'd get destination host unreachable. So that's what we kind of have to kind of look at. So what we want to configure here is we want to go through and actually configure OSPF. So to do that, and let's make the font just a little bit bigger here. Make it hopefully a little easier to read. So for configuring OSPF, what we want to do is start by going into our global configuration mode, and then we set up um, our OSPF configuration. So we'd say router OSPF, and then we just have to set a process ID, as we should remember. So this process ID is any number between 1 and 65,535. This number is only locally significant to the router itself, meaning that it does not matter what number I pick. And also, these numbers do not have to match between any of the other routers. Again, it's just a process ID. It's only locally significant to this specific router that I'm functioning on. So if I want to make any changes to OSPF on this router down the line, I have to remember what my OSPF process ID number is. But that's it. That's the only reason we have to kind of pick this number. So, I mean, I typically just pick 10. It's just how I learned. It's kind of just muscle memory at this time to just do OSPF 10. So the next thing that we have to do when we're setting up our OSPF is we actively configure and advertise each directly connected network that my router is currently touching. So router 0 here is physically touching the 10.0.0.0/30 network, the 10.0.0.0/ or 0.0.8/30 network, and the 192.168.10.0/24 network. So a quick way to kind of verify and go, okay, well, once, and this only works if all of your configs are, at least addresses are set and lights are all green. But a quick way to kind of verify and go, okay, well, what networks do I need to advertise if you don't have this in front of you or you haven't labeled your networks, is you can do a do show IP route, and every network with a C next to it, C, remember, stands for connected, that network is what we have to advertise in our OSPF configuration. So we need to advertise network 10.0.0.0. And then remember, our 30 there is our network mask. So that defines how big or what range of IP addresses I have left to deal with. So it's a shorthand way of writing out our mask, which would be 255.255.255.252. Now, one thing to note though is with OSPF, it will work if I enter in a standard mask. OSPF is smart enough to do a conversion and go, okay, well, I know that's not what I can't actually read standard masks. I can only read wildcard masks, but it's smart enough to convert a standard mask into essentially our remainder, which is a wildcard mask. Now it will work like that, but the better practice whenever entering in a network is to always enter in a wildcard mask. So that's our best practice. Um, if you're kind of looking at it and you're like, okay, well, I don't quite understand wildcard masks or anything along those lines. If we look at, say, like a general standard mask, so a /24 network. So let's go over kind of a general standard mask. So remember, if I'm looking at, say, a network like 192.168.10.0, what this wildcard mask is, or what the standard mask is telling me as a /24 255.255.255.0, is that, remember, each octet has 8 bits inside of it. So I have 8 bits in each network. Numerically, what each of these 8 bits represent is they have a numeric value associated. So we have 128, 64, 32, 16, 8, 4, 2, and 1. And the other thing to kind of remember is this is where kind of binary gets into play, is we have 1 and 0, where 1 is the equivalent of being on and 0 is the equivalent of being off. So when I say that I have a 255, it means that all 8 bits in a given octet are in an on state. So it means that all of these bits are locked and I can't touch them. I can't manipulate them in any way, shape, and form. They're all locked. So if you add up each of these bits, you get 255. So that's where our 255 comes from. So when we look at our other octets here, and we're saying 255, 255, 255, we're saying the first 3 octets are fully locked in place. However, when I say 0 there, remember it means that the all 8 bits in the last octet are free and available for me to manipulate. So I have 255 IP addresses available to me. Really 254 because there's a broadcast address, but I have 255 total IP addresses that exist in that octet. So that's what we see when we're dealing with this. So what a wildcard mask is it's the another way of just saying it's the remainder. So if I have 255, 255, 255.0, and this is a standard mask, then my wildcard is just the remainder. It's what do I have left? Well, I have 0 left in the first octet, 0 left in the second octet, 0 left in the third octet, but I have 255 left in the last octet. And so that's our wildcard. It's just the remainder. So when I'm writing in my mask for this, and you can see I have a 0003, that's because my network for this is 10.0.0.0, and it's a /30. So remember what a /30 means for me is if I look at my actual mask here, it's a 252. But if we say go through the same process here, essentially what that means is the first 6 bits are all locked in place, but the last 2 are available to me. So if we're again counting at say like a /24, we're working in the 4th octet, the 25th bit is locked, 26th bit is locked, 27th, 28th, 29th, and 30th bit are all locked and I can't do anything with them. But the last 2 bits are free and available for me, so that's where our /30 is. So our remainder, if that's our standard mask, our wildcard mask is, well, I have 0 left in the first octet, 0 left in the second, 0 left in the third, and then remember I have a total of 255. I have 252 there, so I only have 3 remaining, and that's my wildcard mask. So again, don't let it confuse you too much. Wildcard is just the remainder of what a standard mask is, but it's good to know pretty much how to go through this and how to come up with this. Cisco does like to ask you questions on these types of things. And then same thing, if they're asking you for any configuration style questions on OSPF, they'll give you likely something along the lines of say like network 10.0.0.0.0.0.3 area 0, but then they'll also likely give you an option of say something like which one is, they're basically asking which one is correct and say, okay, is it 10.0.0.0 with a wildcard or with a standard? In the real world, both are correct. What Cisco wants is the most correct answer, which is use the wildcard when you're advertising networks. So just keep that in mind when you're going through and setting this up. Again, configuration wise, both work. There's no problems if you do it either way, but if you're taking a test with Cisco, make sure that you remember to use the wildcard mask. And it's just good practice to make sure that you do it anyway. So getting back to what we have, so we've advertised our 10.0.0/30 network. Now the other one that we have to advertise is our 10.0.0/8 or 8/30 network. So we'll advertise that network. And then the final directly connected network that we have is our 192.168.10.0/24. So we're going to advertise that network as well. And remember, it's a /24, so my wildcard for that is a 0.0.0.255. So those are my 3 networks that I need to advertise. Now, the next thing that we kind of want to look at is if we do a question mark, there's a lot of different configuration and different items that we can kind of look at. So I talked about router IDs, so let's look at what a router ID does for us. So right now, if I take a look at my router configuration and I say show show IP OSPF, I could just do show IP OSPF, and the router ID that you'll see is the highest IP address on the current up and up interface, which is 192.168.10.1. Well, I want my router to have a higher or to have a manually set router ID. I might not want router 0 to be the designated router. I might want it to be, say, like a backup designated router, or I just want it to be a druther. So I want to go ahead and change that. So to change that, we can go into router OSPF and then our configuration, and we use the router-id command to manually set a router ID. So I can set it to be like, let's say I wanted this to be, say, the backup designated router. So I'm going to be setting up, and I want router 1 to be my primary. So I want it to have a router ID of 3333 for router 1. And router 0 here is going to be my backup. And router 2 down here is going to be my druther. So that's what I'm going to set up. So I'm going to set up the router ID to be 2222. So we'll set up to 2.2.2.2. And you'll get this error message, or not really an error, but more of a warning message that will essentially say, hey, you just set a router ID, but it's not going to take effect because we've already gone through the OSPF process and then we're in a full state. So all routes have been shared. The election process has already occurred. We've already done all this, so you can't change. So what we'll look at is if we say look at do show IP OSPF, you can see the router ID is still the same. So it didn't actually hold. So to change this, we can go back to our standard config here, and we can type in the command clear IP OSPF process, and this will redo the initiation or the election process and basically force this router to rebuild and go all the way back to the init state and back through to determine what its router ID should be. So again, if we look at our show IP OSPF process, we can see the router ID is 2.2.2.2, just like we wanted. So yay. So again, looking at our configs and looking at kind of what we've done right now, You advertise your directly connected networks. And again, to verify what networks are directly connected, you can look at your routing table. Again, this only works though as a way of if all of your interfaces are currently in an up and up state. So just keep that in mind. Otherwise, your routing table won't show anything at all. But it's a good way to kind of verify what you need. And then to set a router ID, it's a configuration underneath the OSPF config, and it'll hold it from there. Otherwise, likely it will grab it from the highest up and up interface, or if there is a loopback set, it will grab the IP address set on the loopback interface. So there's other configs that we're going to go over, but that's good for right now. So let's go in and configure our other routers. And so let's go over to router 1 here. And on router 1, we're going to do the same thing. So we're going to say router OSPF. And just to prove that this process ID doesn't need to match, we're going to say router OSPF 20. So again, it's a locally significant number, doesn't need to match any device. So again, if I'm looking at this, I'm going, okay, well, which networks do I need to advertise on this router? Again, quick, easy way to verify. When all lights are green and all IP addresses have been set, we can look at the show IP route command, and I can see I need to set the 10.0.0.0/30, the 4/30, and my 192.168.20.0/24 network. So we can advertise that pretty easily. So we can go network 10.0.0.0, the wildcard mask for a /30 network. And then remember, our area is our backbone area, so it's our single area that we use. So we're specifying area 0. And then we're also going to advertise our 10.0.0.4 network, which is the network going down between router 1 and router 2 right there. And then we're also going to advertise our 192.168.20.0 network, and it's a /24, so our wildcard is 0.0.0.255. So that's what we look at. So you can see I got an adjacency that formed. Again, what adjacency means is that I've both routers are using router 0 and router 1 are using the same router or the same network. They're using the same area, and they both have the same hello and dead timer. So all 4 of those networks or all 4 of those items need to be correct in order for a router adjacency to actually be established. So same thing, I also want to set a router ID. I wanted this device to be the primary, so I'll say router ID as 3333. And again, remember, because I've already started setting up OSPF, it already went through the process, it pulled its router ID as the highest up and up interface, which is gigabit 02. So my router ID should be 192.168.20.1 currently. And it is. So again, to fix that, I put in my router ID that I wanted, and I will just type in the command clear IP OSPF process, and we'll say yes, and you'll see that it will detach it. This actually forces the router to go back through the initial or the entire OSPF process, so it goes back to init state all the way through all the steps back until it gets to full, where we actually see the configs. And then my final router, we're going to configure here. Again, like I said, process ID doesn't matter. To prove it, I'm just using 30. I could have used 10 on all of them. It doesn't matter. It's just a process ID. It's only locally significant. So again, we're going to add in or advertise our directly connected networks. So my 3 directly connected networks are the 10.0.0.4/30 network, the 10.0.0.8/30 network, and the 192.168.30.0/24 network. So one thing that we can do is we can do a router ID, and we'll say 1.1.1.1. And so what this should do is, because I haven't formed an adjacency with anyone yet, immediately, instead of having to go and do the clear IP OSPF process before I've advertised the networks that I know about, that should take hold. And so when it does start to form an adjacency, it should already have its correct router ID, and I won't have to reset the process. If you don't do it first, it's not the end of the world. Just remember that if you want it to have the correct ID, you have to do the clear IP OSPF process if you've already advertised networks. So we'll do the same thing, 10.0.0.0.4, my wildcard, and then we'll also advertise our 8 network, and then we'll also advertise the 192.168.30.0. And you can see adjacencies are forming. We'll get area 0 in there. And you can see they did get the correct router IDs too between things, so that's good. So now, if I look at my routing table, we should see OSPF routes that have been populated between all of these devices. So we can see that the 10.0.0.30 network has been added. Both the 10 and the 20 networks have also been added as well. Other important things to kind of note when we're looking at this is, again, 110 is our administrative distance, where 2 is what our metric actually is as well. Again, the one issue that we run into with the metric side of things with OSPF by default is that OSPF does not know how to properly differentiate between, say, a fast Ethernet interface, a gigabit interface, or a, say, 10 gig interface. It sees all 3 as being the exact same cost, and that's based off of how it specifically calculates that. And so that can be a little bit of a problem, but I'm going to show you here shortly how we can actually change this. Now, there's other things that we can do in the router process to basically determine which one's going to be the designated router and backup designated router or druthers, and that's with a priority number as well, but I'll get to that in a little bit as well. So overall, everything should ping right now. So if I go from PC0 over to, say, PC2, first one fails because of ARP, but then everything should be successful after that, and it is. PC0 should get to PC1. ARP will fail the first one. Everything else works after that, so we have successful and success. So another thing that's important to kind of do when we're setting up OSPF is we need to make sure that we're only advertising or sending out OSPF multicast messages towards devices that are going to be that need to participate in OSPF. So we'll go back into router OSPF 10. And if we look at our commands and what we can do here, the first thing that we can look at is we have an option called passive interface. And what this does is it suppresses routing updates on a given interface. So it essentially says, right, don't send routing updates towards the out of this specific interface, only send it towards these other devices. This is important because our PC0 and our switch 0 over here on the left-hand side do not need, nor will they ever know what to do with any OSPF multicast messages. So they'll just drop that traffic. But if that traffic's being sent out and I have, say, like a passive listener set up using, say, like Network Miner or Wireshark, I can capture those OSPF routing update messages, and I can actually see general parts of what the actual network is going on. So now this is really only a big issue if, say, like I already have physical access to the network and it's just not configured properly. That's where a little bit of an issue can occur. But for most things, it's not that big of a problem in the grand scheme of things. But it's still good practice to do, if not for a security standpoint, also for just a general network congestion standpoint, to ensure that additional routing updates aren't being sent out and additional resources aren't being used to forward out messages towards devices that aren't going to need to know what to do with those messages. So we can do this in one of two ways. I'm going to show you one way on this router, and then I'll show you the other way on another router. So we can use the passive interface command, and then we can just type in we have a couple options, but we're just going to state the interface that we want to place a passive interface on, which is G02. And now this will stop any routing updates from going out G02. Now, if you place your passive interface incorrectly, so if I placed it on, say, G01, what that will do is it will break my adjacency between router 0 and router 2 down here, because gigabit 01 will no longer be sending out any routing updates or any OSPF messages out towards router 2. So that can be bad. And you can see as soon as I did that, my network adjacency between myself and router 2 down here went down. So if you accidentally do that, it's not that big of a deal. You can just press up on the arrow key, pull up the last command you entered, and then just put no in front of it. And you'll see that in a minute, my adjacency will come back between the two sides and everything's fine. Now, the other way that we can do this, and this is kind of more of what we see with, say, like a firewall approach. So now I'm over on router 1, right-hand router there. If I go into my router OSPF 20 again, I can also say passive interface default. And now what this command will do is it will place passive interface on all interfaces by default. So if I do that, all interfaces will now go down. And if I want to make sure that my current interfaces, or the interfaces that I want to be able to do things on, I can say no passive interface G00 and no passive interface G01. And then that keeps G02 down. So this is good for if I say I have a device that has a large number of different interfaces, and I don't know what grand scheme of things, which ones I want to send OSPF messages out. I just want to play it safe. We can start with all interfaces blocking OSPF and then poking holes where we need. So if I look at my actual configuration of what it looks like, you can see specifically the passive interface side of things, passive interface default, all things are there. And then I've opened holes for 00 and 01 to allow OSPF messages to go through. This is basically just a matter of both ways are correct. It's kind of a matter of personal preference on how you want to do this. I think it's probably a better way to always block everything and poke holes where you need. For general labs, though, it's faster to just say passive interface on a single interface. It is what it is. Okay. So next thing that I kind of want to show you is if we have, say, a default route and also a loopback interface. So remember, again, a loopback interface is just a testing interface. So I can create a loopback interface by just going into one or kind of creating it. And that's by using the interface command. And we can say loopback and then a number that I want to give. And you can create a large number of loopback interfaces. I'm just going to pick 0. So what this does is it brings up a testing interface. So essentially, is if we think about it, there is a line right up here that now exists, and that is going to be our testing interface, which is loopback 0. And this is where we assign, say, a as if it was the internet or something like that. So I'll assign an IP address of 50.0.0.0.1 or 0.0.1. I think I said one too many zeros there. So to do that, it's just a normal interface now. So we just say IP add, and we type in 50.0.0.1, and then tell it how big that network is. And that's it. And I don't have to enter in no shut because by default, our ports start, all loopback interfaces start in an up and up state. And you can see that too, where it goes state change to up. So that's good news. Now, the one thing to remember with OSPF is known as an interior gateway routing protocol, meaning that it doesn't work on the internet. It only works for your internal LAN or private network ranges. It's not designed and does not function on the internet. So you cannot use it on the internet. So therefore, a couple things that are important here is that we, one, don't advertise public routes. So if I'm in OSPF, even though 50.0.0.1 is considered a connected route, we're treating that as if it's the internet. So I'm not going to advertise it in OSPF. Vice versa, I also want to make sure I'm not sending routing updates out, which is where our passive interface default command comes into play. So if that was actually, say, like an internet connection out, it would be blocking all routing updates from going out by default. And only, again, right now, routing updates are only allowed out 00 and 01. So the next thing I'm going to show with why we can use, say, like a loopback interface is for, say, advertising a default route, or also known as a gateway of last resort. So by default, if I look at my routing table, and if this router receives traffic for, say, trying to go to the 50 network, it knows where to go because it's connected to it. But if we look over at, say, router 0 here, and we look at its routing table, and let's say PC0 wants to get to the 50 network on 50.0.0.1 or further out towards, say, the internet, what happens to that traffic? Well, that traffic goes to the router. The router looks, strips off the layer 2 header, looks at the layer 3 header in this destination address, and it goes, do I know where 50.0.0.1 is? Well, it compares it against its known routing table, and it goes, no, I don't know what to do with that, so it drops the traffic. Well, we don't want it to do that. We want it to be able to actually get out to the internet. So because router 1 has a route or has a connection out to, say, our theoretical internet right there, what we're going to do is use our, or create a gateway of last resort, also known as a default route, and then we're going to share that route via OSPF. So we can do that by saying IP route. And remember, a gateway of last resort is just a all zeros. It's what's known as a catch-all address. So it's basically saying, no matter what, if it doesn't match any of these, then use this. And then we're going to specify where to go. And we're just going to shove this traffic out our loopback 0 interface. So we'll basically say, so if we look at our routing table, we can see that we have a default route now. And no matter what, a default route always is the last route read in any routing table. So our router will always read from top down and try and find the best matching route. And only if it does not match any of the routes that exist in its routing table, then and only then will it use the gateway of last resort, which is our default route right there. So to share this route out with our other routers, we can go into our OSPF configuration, so router OSPF 20 on this device, and we can use the command default information originate. And what this command does is it essentially says, I have a default route or a gateway of last resort, and I am going to advertise it along with the rest of my routing table towards other devices that are using OSPF. So now if I go back over to router 0 here and we look at our routing table, we can see that we do have a new OSPF route, but it has a specific extra couple of flags there. One, the star means that it's a candidate default route, so it is a default route. And the E2 means that it's an external type 2 or OSPF external type 2 route, which means that this is a route for how we leave our LAN, how we get out of our actual network. So if I don't know what to do, I'll send it here. So that route should also now exist over on this side. So now if I go over to say like PC0 here and I ping 50,001, it should work just fine, and everything does. So that's a general gist of a lot of the OSPF side of things. Let's get into just a little bit more. Sorry, I have just a couple tabs open. So let's get into a little bit more of our configs here. So we've looked at router ID. Again, I talked about the router ID process. Remember, it starts with, is it configured? If no, it goes to loopback. If that's not configured, it picks the highest IP address on an active interface, and then it uses that as its router ID. Typically, you want to avoid it picking that. We've talked about this. Remember, our router ID is a 32-bit number, so it's just an IPv4 address. So you can pick anywhere from 1.1.1.1 all the way up to all 255s. Recommend not using that. Probably stick with something like what I did, which is like 3333, 2222, 1111, just to keep it a little easier for yourself. Again, kind of showed that as well. So we're going to do kind of a 1-2 skip a few as we go this. So talked about wildcard masks. So let's went over passive interfaces already for all of you. So let's see. We talked about that. The one thing to remember with OSPF multicast messages is there are 2 default multicast messages. So it's 224005. That number is used by the designated router and the backup designated router. And then it also uses 224006 as well, but those are for druthers. So all druthers will listen on the 224005, and the DR and BDR will listen for response messages from the druthers at 224006. So moving on, I think the next part that's kind of important to kind of go through is looking at the cost metrics. So cost metrics are the next kind of important aspect. So remember, OSPF doesn't know how to differentiate between the two things. You don't need to know too in depth between what the actual how it's actually done, but it's essentially just division. So it's dividing the reference bandwidth by the interface bandwidth. And that's essentially all it's doing. So again, based off of that calculation, based off the default bandwidth or the default calculation of the reference bandwidth, it doesn't know how to differentiate. And so the numbers of what it calculates out all equate to 1. So it doesn't know how to differentiate between 100, 1, or a 10 gig line. So how do we change this? So it can't go lower than 1, which is why even though those divisions go to say like 0.1 or 0.01, because it doesn't know how to differentiate between that, and it doesn't know how to deal with non-whole integers. It rounds up to the nearest integer, which is going to be, say, 1. So looking at this, we can change the reference bandwidth by using the auto cost reference bandwidth command, and that makes actual changes to the interface itself. So if I wanted to, say, set a port to be identified as a 10 gigabit Ethernet interface, on that interface, so I'd actually go into, say, int g00, and I would say auto dash cost reference dash bandwidth 1000. Um, oh, that's for a gigabit, sorry. And for a 10 gigabit, I would go auto cost reference bandwidth 10,000. And then if you want those reference bandwidths to go back to default, the number is 100. So that's kind of the primary thing. No, if you want to take anything out of this, just know that the default is 100 for 1 gig. If you want to change it, it's 1,000. For a 10 gig, it's 10,000. So that kind of should be the primary aspect of it. So for how it's actually calculating the best route based off of SPF, essentially what it does is it calculates out cost based off of that router's perspective in order to get to the best place. So for router one's perspective, if it wants to get over to this network of, say, 10.10.3.0/24, it will add up the potential costs of the different ways to get there. And then it will take the lowest additive cost and add that into its router from its perspective. So it's not looking at the perspective of where is the end device that exists at, say, like the 10.10.1.0/24 network. It looks at router 1, and router 1 goes, okay, in order to get to 10.10.3.0/24, which is all the way over on the right hand side of router 3, it'll add up and it'll go, okay, I can take the immediate hop from myself over to router 3, that's 10, and then to get to that network, that's 1, so my total cost would be 11. But do I have a better route? And it'll also go, okay, well, I can also get there by going up to router 2, which is a cost of 10, then down to router 3, that's a cost of 20, and then over to that network, so it's a total cost of 21. And then it compares the two potential routes and it goes, okay, well, the cost of 11 is less than the cost of 21. So therefore, my direct route and the route that's going to be added into my routing table is my route going from router 1 to router 3 to get to the 10.10.3.0/24 network. So that's our general overview of how it kind of goes through. Now, this secondary route doesn't get thrown away. It still exists in my OSPF database, but it will only get pushed into my actual routing table or my routing database if the link between R1 and R3 goes down. And if that link goes down, then the SPF algorithm reruns, checks for backup links and the next best route to still get to that network, and then adds that secondary route into the routing table. So again, that's our metrics. That's how we kind of go through things there. Hello and dead intervals. So with hello and dead intervals, the default timer for a hello is every 10 seconds, and the default dead timer is 40 seconds. So again, all that means is every 10 seconds, my router is going to send out a hello message, which is essentially a keep alive to check and make sure that both sides are there. And then the dead timer is there to basically say, if I don't receive a hello within 40 seconds, which is 4 times the hello message, then I'm going to consider this line down and I'll cut the connection. So that's the default. Now, hello and dead intervals, You can change this, so you can lower them or you can increase them. More times than not, you'll probably just leave them alone, honestly. The reason you might want to change them is if it's, say, like a very important connection, um, or if you're not too worried about some additional overhead on resources or packet management, it's okay to lower that. You might want to increase it if, say, you're on a slower connection, say like a T1 line, and you need to make sure that you're leaving as much available bandwidth as possible, and you could increase the hello and dead timers. All right. Let's get to the last item. So if you wanted to change that, it's IP OSPF hello dash interval from and then dead dash interval. And then to reset them, it's the exact same command, just put no in front of them, and it'll set the hello and dead timer back to default. Okay, we talked about default route propagation. I think that's pretty much it in grand scheme of things. Last thing, yeah, so that's about it. So all these slides are available. I kind of hit the highlights and did most of these slides as a demo. So if you do have questions on anything, again, feel free to reach out to me. I'm more than happy to help out. All right, have a good one.